everybody, my name is Tatiana and welcome to my video series on OTF Studio thin film software, a modern, smart and powerful software for designing, characterization, reverse engineering and monitoring of multi-layer optical coatings. Post-production optical characterization or reverse engineering of produced multilayers provides feedback to the deposition process. Reliable reverse engineering results enable adjustments of deposition parameters and finally improvement of production quality. In this video, I will demonstrate how to perform reverse engineering of a fabricated multilayer using OTF Studio thin film software. In this example, I will perform reverse engineering of a Beamsplitter consisting of 10 layers. Layer materials are germanium and terbium fluoride, typical for infrared and near-infrared spectral range, and the substrate was zinc selenide. In my disposal, I had experimental measurement data, experimental transmittance, measured at Brewster angle, 67.9 degrees for zinc selenide, S&P polarizations. Also transmittance at normal incidence, and reflectance, quasi-normal incidence 8 degrees, 45 degrees S&P polarizations, and Brewster angle, also S&P polarizations. I open my OTF Studio project, first in analysis and synthesis mode. Here, we can see it here on the quick access toolbar. And this is my 10-layer design, 10 layers of terbium fluoride and germanium. Terbium fluoride layers are thicker and germanium layers are thinner. This is reflectance S&P polarization at Brewster angle of zinc selenide substrate. And also there is a second operation range from 4 to 8 micron and transmittance at P polarization at Brewster angle must be close to 100%. And then I switch to reverse engineering mode using quick access toolbar. This is very fast. And now this is reverse engineering mode. The reverse engineering mode, I see experimental reflectance at quasi-normal incident 8 degrees and theoretical reflectance. And it's seen that there are deviations between experiment and theory because of errors in layer thicknesses. Also, I can load transmittance at normal incidence, and there are deviations between experiment and theoretical transmittance data. For reliable reverse engineering, I need informative features and measurement data. I need more measurement data. So I will combine measurements for reflectance 8 degrees, reflectance S and P polarization 45 degrees, and normal incidence transmittance. I mark these measurements, press combine, and press combine again, and give a new name, for example, combined, for this new measurement data file. And I load these combined measurements and have two plots. One is for transmittance and one is for reflectance. But for transmittance, I also can add legend using standard design editor, chart editor, and now I can start reverse engineering. In this reverse engineering problem, a systematic errors model can be applied. This model assumes that all terbium fluoride layers exhibit an error, the same for all terbium fluoride layers, And all germanium layers also exhibit the same error, delta germanium. So if we have a look at the relative errors plot or diagram, we can see that all germanium layers exhibit one error and all ytterbium fluoride layers exhibit another error. Internally, there is a discrepancy function which estimates the closeness between experimental and model reflectance and transmittance. And this discrepancy function will be minimized regarding to these two parameters, delta for ytterbium fluoride and delta for germanium. In OTF Studio, all reverse engineering models and algorithms are controlled through reverse engineering model builder panel. I check here a systematic thickness model, and if I open this panel, I check activate error for ytterbium fluoride and for germanium. And notice on the bottom of this display the discrepancy is 8.6 approximately. And then click on run reverse engineering, and very fast we obtain discrepancy 1.3, so many times smaller, and very good fitting of experimental data by model data using two model parameters. Let's have a look at obtained errors. View thicknesses panel. I combine reflectance and transmittance plots to save the space. And relative errors in germanium minus 6.5% approximately, and small errors in the ytterbium fluoride layers minus 0.5%. It means that both materials were under-deposited in this deposition run. This multilayer was supposed to operate at the Brewster angle. For additional verification, I will use Brewster angle measurements. So I load measurement reflectance and transmittance using append feature. And here in this plot, we can see all measurements all together, also for Brewster angle and for other angles. And this is reflectance plot, and the same can be done also for transmittance. It's already here. And we can see also very good correspondence between results for Brewster angle as well. How to use these results practically? We have these relative errors. We can calculate correction factors and use these correction factors to adjust tooling factors in the deposition plant. This is one possibility. And another possibility is to use these values to recalculate the design, to adjust the design to tooling factors that exist. In OTF Studio, there is a recipe, design recipe feature in the results ribbon recipe, and we can save the new design that is already adjusted. So this is old design, initial design, and this is a new design. Commit, and we will have two designs in the database. One is initial and one is new. So this is initial design, and we can open also the new design, compare them, and we can see that their thicknesses are slightly different because of this adjustment of the design. Thank you for watching. If you have questions, please contact me, and see you in the next video. Bye!